hear so many of you. We start today the third lecture in our series organized by the Department of Physical Development, and it's my pleasure and honor on behalf of the organizing committee to welcome today Professor Francis Halzen from University of Madison, Wisconsin, who will give a lecture on the IceCube, the experiment IceCube and discovery of high-energy cosmic neutrinos. And today we will have a unique opportunity to learn something from one of the pioneers, one of the creators of this particular field. Before we start, let me ask Professor Nick Van Remortel to introduce Professor Francis Halzen in more detail.
Thank you, Igor. Welcome, colleagues, friends, ladies and gentlemen. It's a great privilege and a great honor for me to introduce the career of Professor Francis Halzen here to you. Professor Halzen has currently the American nationality, but he has Belgian roots. He is born in Tienen, if I remember correctly, and he obtained his PhD, his doctoral degree, at the KU Leuven in 1969. After some postdoctoral work at CERN, he moved to the University of Wisconsin at Madison, where he became a full professor in 1977. Now, Francis is a Hilldale and Gregory Wright Distinguished Professor at Wisconsin in Madison. Now, together with Alan Martin, Francis wrote a seminal textbook on particle physics, which is this book here. It's been used for many years in the curriculum in our own university here. It's a standard work written in 1984, but it's still used in many curricula all over the world. Now, Professor Halzen is this year with us here in Belgium quite often because he received the joint University International Franchi Chair for the academic year 2014 and 2015, awarded by the VUB, the ULB, University of Kent, Mons, our university, the University of Liège, and the KU Leuven. Currently, although Professor Halzen has a large research track record both in theoretical and experimental particle physics, he in fact started working on the theory of QCD back in the days, but currently is mostly known for his work on neutrino astrophysics, or astroparticle physics as it's often called. He's the principal investigator of the IceCube experiment, and he's also the director of the related institute at Wisconsin-Madison. Francis started this project in the 1990s and came up with the idea to build a giant neutrino detector in the Antarctic ice. It started with a small, relatively small-scale project called the Amanda experiment, which started in 1994 and ended in 2009, and now has grown out to a massive detector of several kilometers in size, which is now called the IceCube experiments and its extensions. The current version of IceCube was completed in 2010, and in 2013 it discovered one remarkable phenomenon, namely the first ultra-high-energy extraterrestrial neutrinos, of which we will most likely hear more about. Today, the IceCube experiment consists of about 250 researchers in 40 institutes and spread over 4 continents, with also involvement from Belgian groups, which contribute about 10% of the collaboration. I want to conclude with this. Francis will probably surprise us with some whole of the press result of his experiment, and I'm looking very much forward to hearing it.
Thank you very much for this kind introduction. It's for me a real pleasure to be here and to come and thank you for supporting me for the Franchise Chair. And so the subject of my talk is not going to be QCD, it's going to be IceCube. And so I will start my talk by answering the question which you probably, all want to hear the first answer to. Why would anyone get the idea to build a kilometer cube particle detector? But there was a good reason to do this. Then I will tell you about the construction of IceCube and how, when the experiment was completed, we discovered cosmic neutrinos in the first 2 years of data. And then I'm going to conclude by saying a few words of what we want to do next. Now, neutrinos are strange particles because we have answered the question what the world is made of. The world is made of protons, neutrons, electrons, and neutrinos. Protons and neutrons we now call U and D quarks, and there are more leptons and more quarks, but that's irrelevant to this lecture. These are all the particles you have to know. And the neutrino, most people are never told about neutrinos in high school. They are actually the most common of these particles. And they were discovered in 1933 in the following way. Ellis and Mott at Cambridge did an experiment where they were watching the decay of a neutron. And so a neutron would decay into a proton and an electron. And so they would occasionally see that the proton and the electron would move in that direction, which meant that either momentum and energy were not conserved, or it meant that there was another particle going in that direction. And that particle was the neutrino. It had in fact been postulated already by Pauli. And this is what we call today a missing mass experiment. And so that's how we did these days, like we look for supersymmetric particles this way at the LHC in Geneva. But people couldn't imagine they had discovered a new particle. So we had to wait until 1956 until this discovery became complete. Now the other thing is, so you see, neutrinos you have to think of as an agent that is present wherever neutrons change in protons, and the other way. So neutron changing in protons, that's called nuclear physics. And so neutrinos have a hand in wherever nuclear processes are happening, which we'll come back to later. So I told you they're the most common matter particle in the universe. And so in fact the universe, which we now understand in terms of dark matter and dark energy, and which we can model in detail, without neutrinos the universe would look completely different. In fact, here you see a picture of a universe with neutrinos and without neutrinos. And without neutrinos it would look like on the left, with neutrinos it would look like on the right. And so when we map galaxies today and clusters of galaxies over deep distances in space, we know the universe looks like that, not like that. As the neutrinos barely interact, in fact, Pauli said, I've discovered a particle that will never be detected. He was fortunately wrong. As they barely interact, they stream through the universe over long, long ranges, long distances, and they erase small-scale structure. And that's why these two pictures look different. So there are about 1,000 in my thumb, and by that I mean in my thumb and next to it and in the whole universe. And so this is one example of the fundamental role played by neutrinos even outside nuclear physics. But this was a big event in neutrino physics in '87 and truly the beginning of neutrino astronomy. In February '87, this star, which you see in this picture on the left, the next day looked like that, and that means the star exploded. Its nuclear reactor in the center, like this one in the center of our sun, couldn't support the gravity of the matter of the star anymore, and 99% of the energy at that point of the star, the solar mass, is released in neutrinos. And in fact, detectors that were built for all kinds of other things captured 24 neutrinos. And of that, thousands of papers were written on these 24 events. It tells you the power of information that you can get out of a few neutrinos. And we're kind of reliving that today, as you will see in my talk later. But so in '87, the idea of doing neutrino astronomy already existed for a long time. In fact, Reines, who gets officially recognized, he got a Nobel Prize for discovering the neutrino by putting a detector close to a nuclear reactor, which of course produces a lot of neutrinos. Reines told me that as soon as he published his paper, everybody had the idea that the neutrino was an ideal messenger for astronomy. Of course, the critical properties are it's electrically neutral. You cannot do astronomy with charged particles, because charged particles, before they reach your detector, they are bent by the magnetic field in the galaxy. And they may have been produced there, but by the time you detect them, they come from there. So the sky is completely scrambled. So that's why we don't know the origin of cosmic rays. They don't tell us where they come from. It's essentially massless. In this talk it is massless. The tiny mass of the neutrino is very interesting for particle physics. In fact, it cannot be explained by the standard model. But in this talk, neutrinos have such high energy that we can forget the mass. So at this point, it's just like a photon. No difference. It's essentially unabsorbed. So it barely interacts with matter. And that's the only place where it's different from a photon. Photons don't go through walls. Neutrinos go through walls. They go through the Earth. They go through your detector. And so it's very difficult to detect them. So that's the trade-off. The pact with the devil of neutrino astronomy. It's a great particle that's given to you, but you have to try to detect it. So why would you want to do, we do astronomy with photons. Why do astronomy with neutrinos? Well, I can illustrate that in two slides. This is a picture of a star that exploded 1,000 years ago. It's the Crab Nebula. The star imploded like I described. 99% disappeared in neutrinos, which are long gone in the universe. A neutron star is left behind at its center, and the debris of the star, you see this picture of the Hubble Space Telescope, visible light. That's what you would see with your eyes. But if you take that picture in X-rays, or in radio, or infrared light, it looks totally different. In fact, if you look at very small wavelength in X-rays, very high energy photons, you see this particle beam appear. It's probably an electron beam that radiates photons, and the photons are in the X-ray wavelength. This had never been seen before until NASA launched the Chandra satellite. And so, of course, astronomers have been doing this for a long time. So they have used up all the wavelength of light that are usable. And so the only thing left is to do this in neutrinos. You need a neutral particle. The other neutral particle is the neutron, but the neutron doesn't live long enough to do astronomy. It decays, as I explained. So the idea is just to take a picture of the universe in neutrinos. And the question is, how big a telescope do you need? And that question was basically answered for the first time by Zatsepin and Berezinski in 1969, and I will go through their argument. So first of all, this is a one-slide textbook picture of astronomy. It tells you how much light there is in the universe. The universe is not an empty place, it's filled with stuff. And of course, most notably here, it's filled with microwave photons, which are the friends of the 110 per cubic centimeter neutrinos that I talked about before. So you see, that's by far the largest flux of light in the universe is in microwave photons. But there are photons in the universe of all wavelengths. There are radio waves, there's even visible light, as you can see here, and there are X-rays here, and these are GeV gamma rays. And then you see photon physics kind of stops. And I will come back to the end of my talk. I think we are beginning to understand in detail why there are no high energy neutrinos. You see here, there are only upper limits. And so the idea is to build detectors that can explore these wavelengths but with neutrinos instead of photons. So, by the way, that's the energy of the LHC. However, at these energies, the sky is not empty. The sky is actually filled with cosmic rays. And if you have to get used to this slide, but this energy is about 10 GeV. And at 10 GeV, there are 1,000 cosmic rays for every photon in the universe. So, cosmic rays, protons, nuclei, dominate the radiation in the sky. And so, by the way, it's very easy to detect photons in this region. You can do it with air shower arrays and a bit of help from muon detectors. This has been tried, and that led to this limit. Nobody has ever seen 1,000 TeV photon. So I will use in my talk TeV as my standard unit. TeV is the energy of the Fermi-Lab beam, and it's a fraction of the energy of the LHC beam. So that's my small unit in this talk. So this was the argument. So here are the MEV neutrinos I was talking about produced by the supernova. They were in this energy range. What we are talking about today is what we were looking for, is neutrinos in this energy range. PV, by the way, stands for peta, so it stands for 1,000 TeV. I will occasionally use that name. So here is Zatsepin's argument. He pointed out that the very high energy cosmic rays, they come from outside our galaxy. They are so energetic, they have about 10 million times the energy, not about, they have 10 million times the energy of the LHC beam. So they are incredibly energetic, and they cannot be contained by the magnetic field of our galaxy. They are not trapped. So they are a population that fills the whole universe. And so he realized that these cosmic rays live since the beginning of time in the same place as the microwave photons. So you can think of the universe as this big thing expanding, being filled by cosmic ray protons, nuclei, and by microwave photons. And if you look at their energies, you realize that whenever one of these cosmic rays meets a microwave photon, they will interact, produce a pion, and the pion will decay into a neutrino. So the universe has been producing neutrinos since the beginning of time, and is still doing this in the whole universe. Now you can calculate how many pions and neutrinos are produced on the back of an envelope, because we know the flux of the beam is the flux we observe at Earth of cosmic rays. We know the density of microwave photons, 410 per cubic centimeter, and so we know the cross-section for P gamma to interact since 1950 something, I think. And so the result is on the next slide. That was the result they got in 69. So the pion decays into a muon and a muon neutrino, and the muon decays further into an electron, a muon and an electron, and a muon and this muon neutrino. So the details are not important. If you build a cubic kilometer detector, they decided you will see one event per year. And that was worth it, because that neutrino will point back at where it was produced, unlike any of the many cosmic rays you see. So they That's the bad news. The good news is that this neutrino has an energy of 1,000,000 TeV. So when it hits your detector, there's no way to miss it, and I'll come back to that later. So I apologize when I said that's all you have to know for this talk. You have to remember there's an electron, a muon, neutrino, and so of course the muon is a heavy electron. We still don't know why it's there, but in this talk I don't care. It's very useful to us, as you will see. So let me say a little bit more. You know, yes, you want to build a kilometer cube detector, but with the argument I just made, you know, there was just not enough to, you know, loosen up the money of the funding agencies. So we started out in the 70s first to do this calculation in more sophisticated ways, always at the same answer. And we started to look for other places that would produce neutrinos. Now this is the only equation in this talk. I talked about charged particles being contained in the magnetic field of our galaxy. What that means is that their gyro radius is smaller than the size of the galaxy. In fact, it's extragalactic, their gyro radius is larger. So, this is the gyro radius of a proton of energy E in a magnetic field B. So it's E over B. Q is the charge of the proton, 1, and V is the speed of light. Everything in this talk moves at the speed of light. So in order to accelerate a particle somewhere, it has to be contained in your accelerator. If you don't contain it in your accelerator, there's no time to accelerate it. So the gyro radius E over B must be smaller than the size of your accelerator, which means that E is smaller than B times R. This dimensional analysis, you need big magnetic fields over large distances. But there's an upper limit that comes with these two numbers. And it's amazing, actually. This is a solar flare. And the sun is covered up here. What you see here are streams of charged particles, relativistic particles. If you have a stream of relativistic particles, you have a current. A current makes magnetic fields, and you can accelerate particles. So if I look up the magnetic field in a solar flare, and I look up its size, and I make the product B times R, I get 10 GeV. And after you wait for a day, 10 GeV protons arrive from a solar flare. So these accelerators are actually, nature finds a way to make this acceleration extremely efficient. We actually do see 10 GeV protons. Of course, we see many more protons of lower energy, but it managed to almost reach this dimensional limit. Of course, the sun cannot accelerate particles of 10 million TeV, so you look for larger objects. Exploding stars again. These filaments you see in X-ray picture of a supernova, those are exactly streams like you saw in the picture of the sun, except that this object is much bigger, it's a higher magnetic field. So we believe actually that these can accelerate the cosmic rays in our galaxy. If this star had collapses to a black hole, it creates an object like this, but it does it in 1 second. This took 1,000 years. And that's called the gamma ray burst. And so here is a simulation of it. It doesn't matter what this picture is. And so slowly we imagined objects like this as well. This is an active galaxy. It's a galaxy like ours, but it has a billion solar mass black hole in it. And in the gravitational energy around this black hole can be transformed into acceleration. And so this is all very complicated, but you know, you use this B times R formula, and these are the places where you can go and look for particle beams in the universe. And so wherever there are particle beams, there are neutrinos. At CERN there are neutrino beams because people take the accelerator, shoot the protons into a block of steel. In the block of steel you produce pions, and the pions decay in neutrinos, so the neutrinos don't interact, they come out, everything else gets absorbed in the steel, so you get a neutrino beam. It's the same, everything I mentioned, black hole, neutron stars, they are all objects that are surrounded by light and by dust. So the accelerated particles will move through targets of radiation and dust. And so if they make the cosmic rays, I know the beam, I can ask the astronomers about how many photons there are around a specific black hole in one of these models I mentioned. And then I calculate a way protons interact with gammas, make pi pluses that decay neutrinos. Now, important, I come back to this later, there is another reaction where the proton makes a pi zero. So for every neutrino produced, if you work this out or you count on your fingers, for every neutrino you produce in these sources, you produce a gamma ray of the same energy, roughly the same energy, within a factor of 2. Remember that. So here is the result of calculations by many, many theorists for a long couple of decades. And so what you are looking at is the predicted flux in neutrinos as a function of their energy. These are the results. These are the results for supernova remnants, this grey band. This is the prediction for gamma ray burst. And this is the prediction for this one neutrino per year of enormous energy. You see, we are here at many, many TeV. So the fluxes are flat lines because these fluxes in these models fall like the energy square with energy. And so I've multiplied by energy square. I will do this from now on. So all the theoretical predictions look flat. And so that's easy, that's the result. Unfortunately, if you now work out how many events I get from these predictions in this decade of energy, it's 10 to 100 events per year. It's better than 1, but it's still 10 per year. The other problem is you have to believe these calculations. They are modeling, they are not quantum electrodynamics. So this was a gamble, and so, but the world decided it was ready for this gamble, so we built IceCube. Now you wonder what this is. Well, this is very important too, and not to be forgotten about. What this is shown on the next slide in detail. This is cosmic rays again. They hit our atmosphere. When they enter the atmosphere, they meet nitrogen and oxygen nuclei, produce pions. Pions decay in neutrinos. So the atmosphere is a source of neutrinos. As I stand here, IceCube detects one neutrino every 6 minutes. And we wish we didn't. Or certain people are happy about this because they do particle physics, but that's something else. So the sky is a background of neutrinos all the time. And not just neutrinos, remember, you also have to know about the muon. So with the neutrinos, muons are produced. And, thousands of muons go through this table here, this lecture, every second. And that's why we build neutrino detectors on the ground. But if you build them big enough, this is still a problem, as you will see later on. And so that's, on this slide, that's the background neutrino flux. Now notice, when you come to this energy, this is 100 TeV. At this energy, this flux dies away. So if you can catch neutrinos that are of energy that's larger than 100 TeV, the sky is totally empty. One event is a discovery. And that's, of course, what we were looking for. You can do physics here, but it's in a large background, it's very difficult. Now remember this plot. So how do you build IceCube? I built a kilometer cube detector, and that was figured out in 1960 by this man. And his idea, instead of reading this, his idea is shown in the next slide. So you go underground. You could, in principle, build this experiment on the surface. It just costs too much. But you go underground to get rid of backgrounds, radiation of cosmic ray muons. Neutrinos, of course, go through the Earth. You cannot get rid of them. And so you find, and his idea was to find a lake or a sea, and you go several kilometers deep where it's dark, and the water is clear. So imagine a kilometer cube of some clear, deep ocean, dark, deep ocean water, and you fill it with light sensors. And so the simplest idea is you look for a particle coming through the Earth.